Okay, YouTube, this is our second video on our module in solving systems with three equations and three variables, traditionally x, y, and z is what we're going to look at here. Essentially, what we have is a nice series of steps over here that we can take and use to solve a system that's, we got three equations and three variables, and it looks really complicated. But what I'll tell you is the complicated part is just putting it into words, and we'll read through this, but the process itself is really not that complicated because as we'll read in step number one here, let's look at the goal to begin with here. We say reduce the system in two equations, or two equations and two variables. Essentially, what we want to do is take this thing that has three equations and three variables and reduce it down to a system that has two equations and two variables because, I don't know, I'm just making this guy up here, but imagine we had a system that had two equations and two variables. Well, we have some experience in solving things like this. So all we're really trying to do is eliminate a variable here in two of our three equations and to eliminate the same variable from each of those two equations. And so what we're going to read here is basically our goal is to reduce the system to two equations and two variables so we can solve it more easily. But we say that this is usually accomplished by taking two different pairs of equations and using the addition method to eliminate the same variable from both pairs. So what I want you to notice is, as this is written over here, they label these equation 1, equation 2, equation 3. And as they mention up here, taking two different pairs, what we're really meaning is that we're going to use, say, equation 1 with equation 2. That's a pair of equations. Or we'll use equation 1 with equation 3. Or we could use equation 2 with equation 3. There are only three pairs of equations that exist, but what our goal is to eliminate the same variable from, say, the resulting equation we get when we add the two equations together. And so as I look at this here, we look at our, say, our x's here, our y's, and our z's. Certainly we could really take our pick as to which one we want to eliminate. Just for this video alone, I think that what I'd like to do is eliminate our z's. And just to tell you why I feel like I want to, essentially, I noticed that if I were to add together these two equations right here, they wouldn't eliminate automatically here, equation 1 and equation 2. But I noticed that if I were to take, say, this 2z here times 2, take the whole equation times 2, but take that times 2, it would be a positive 4, and that's going to cancel out really easily with a z here. And so that will work with this plan here. We're going to cancel out our z's. So our goal is to get rid of the z's in two of our equations. So the way this is going to work is essentially this. I'm going to use equation 1 with equation 2. And I want to have a practice here of writing these out at first. We say equation 1, equation 2. We'll just go ahead and write 5x minus 2y minus 4z. This is our equation 1. And that's equal to 3 here. And then we would say that this is 3x plus 3y plus 2z is equal to negative 3. So here's going to be our plan. We're going to eliminate our z's by taking this whole second equation times a positive 2, which is going to give us a new system now. And this new system is going to be still the same first equation. Okay, that's unchanged. And what we did here was we took everything times 2. This would make this a 6x, positive 6y, and then a 4z. A 4z is what we wanted there. And then we have to take it all the way across here through to our equal sign. So we would say this would be a negative 6. And so our goal here was to eliminate our z's, and we've done this. And so look what we get left with here. We get left with 11 x's. Here, when we add together our y's, we'd have a grand total of 4 y's. And we could say that this is equal to, I suppose, negative 3. And I'm going to put a box around this. Now, keep this for later. But one thing I want you to know is this. Because we used equations 1 and 2, we can't use those same two equations again, even to cancel anything else out that would be easy. We are committed to canceling out z's. And so now the question is, do we want to use these two equations here that have these z values, okay? Or do I want to use, say, equation 2 and equation 3, perhaps, to do this? And I'm actually inclined to do 2 and 3 because I feel like I can make these both into a 6. And so you'll notice that what we're doing is making these the same number, but looking for a least common multiple. So when we write this out here, let's write equation 2, equation 3. Annoying, but we're going to write these equations down. We say 3x plus 3y plus 2z is equal to negative 3. And then our third equation here was negative 2x is negative 2x plus 5y plus 3z, and this is equal to a 3. Essentially, we want to cancel out our z's again. But this time you notice we're going to have to take both equations times this scaling factor. So we're going to take the top equation. I'm going to take it times a 3. And the bottom equation I'm going to take times a negative 2 so that this becomes a negative 6 z. So when we rewrite this here, let's go ahead and take a look at the new system we would have here. We'd have a 9x. This would be plus a 9y plus a 6z and then minus 9. And as we go ahead and take everything here in this third equation times a negative 2, we would get a positive 4x, get a negative 10y. We would get a negative 6z. Okay, so you see how that's going to cancel out there, and then we would get a negative 6 over here. So summing these now, we've canceled out the same variable, but look what happens here. We get left with 13 x's. This here would be a negative y, and over here it looks like we would get a negative 15. So I'm going to put a box around this. Now that we've done this, and this was step 1 here, reduce the system in two equations and two variables. We have two equations and two variables. What I want to do is write our new two equation system over here. So we say two variable system. This is what we're going to write over here in this space. And I would write this traditionally underneath here, but I just want to save this space. And so we would say that our new system looks like this: 11x plus 4y equals negative 3, and 13x, minus y is equal to negative 15. And so one thing that I want to comment on here is basically you can go through the rest of these steps to solve this 3x3 system, but I want you to know that from this point onward, it's going to be the same practices that we've used to solve systems in the past. So in step 2 here, it's just going to say solve the resulting system in two equations and two variables using addition or substitution, your choice. And it says the result is an equation in one variable that gives the value of that variable. So essentially, now I'm going to choose to use elimination here, and I'm going to choose to take my second equation times a 4 here, so I get a negative 4y here. But basically, we're just going to solve this and find out the value of at least one of our variables here. So our first equation remained the same. Our second equation here is we distribute this 4. Suppose we get 52x's here. We would get negative 4y's here, and 4 times 15 here, it would be a negative 60. And so looking at this, suppose adding these together, we get a 63x. Our y's cancel, and we get a negative 63 on the right side. So not that this always happens, but this is kind of cool. We get a value of negative 1 for our x. And so a nice pretty value there. And what I want you to notice is basically once we have the value of that variable, step 3 is going to indicate that we'll just take this and plug it back into any of the equations that we used here in our two variable system. So just like we would with a normal two variable system, let's plug this back into one of these equations. Since we're finding y, suppose I'd be inclined to plug it back into our second equation. So we would say 13x minus y equals negative 15, where our x value here, our x value, we know its value now. It is a value of negative 1. And so we get negative 13 minus y is negative 15. As we add 13 to both sides of this equation here, it looks like we get a negative 2 on the right side. So we get negative y is a negative 2. So this would imply that y is 2. And so for number 4 here, it says use the values of the two variables from steps 2 and 3, that we've just done here, to find the value of the third variable by back substituting into the original equation. So any of these equations here, since x and y are going to be the same in any of them, we could plug it back into any of these equations we choose. And so since what we're looking for now essentially is z, I see that this one has the smallest positive coefficient. So maybe I'll use this second equation right here. And so, I would say even below this work right here, I'd finally say, okay, well, I know that 3x plus 3y plus 2z is equal to negative 3. And so what we know now is that x and y have known values, and that z is the unknown value. And so we're going to plug in for x negative 1 and plug in for y our 2. So what we end up with is this negative 3 plus 6 plus 2z, equals negative 3. And what that does is it leaves one unknown that we can go and solve for here. So as we combine like terms here, we would get a positive 3 plus 2z equals a negative 3. As we subtract 3 from our negative 3 on the right, we get a negative 6, so 2z is a negative 6. And so we could solve for z now and say that that's a negative 3. So I put boxes around all of these, but what we want to say is this, is that we got a solution. And so that solution right here is in ordered triple form, going to be written negative 1 for x, 2 for y, and negative 3 for z. So we're going to put a box around this. And one other thing that I want to make sure that we do is indicate that this is a consistent system. When we say a consistent system, it means you got a solution. And because these three planes only intersect at one point, then otherwise we would say they are very independent of one another. So consistent, independent, one solution case here. So what I would like for you to try then is go ahead and this checkpoint 2 here, use the same methods, choose a variable to eliminate to begin with, and then use two pairs of equations to knock it down to a 2 by 2 system and go from there. Cheers.